2, 1, start.
Hi YouTube, welcome to, I've forgotten what week, but chapter 10 of the Introduction to Statistical Learning in Python book club, part of the DSLC. This week was the second week, or the second half of the deep learning chapter. So we're going to go on from CNNs through to the end of the chapter, including the slightly tougher bit at the end, but I'm not going to dwell on it too much, given that it is within the scope of the book, but only just. As usual, attendees in the call live, please do jump in and discuss these things with me. I've got questions and thoughts of what I thought was interesting as we go through. So yeah, please do just shout out and jump in if you disagree with anything I say or want to add anything. So last time we talked about, what did we talk about? Feed-forward neural networks and then deep neural networks. And they all created, or were all fit based on, where are we? This sort of setup, where you've got a linear combination of activation functions or functions applied to each unit. And CNNs tweaks that idea slightly to not have just an arbitrary function, but instead doing convolutions of the layers. And this is used a lot in image data, image classification. So the idea is that the CNN will then find features within the picture that identify that image as a certain object if you're doing a classification job task. I guess the first thing is that you've got your color image, so RGB image, and that gets squashed into a, well, it doesn't get squashed, it gets just kept in the array, but you have a three-dimensional feature map where you've got the spatial axes and then the three color axes. I've written a question there, what does numbers mean? Which isn't grammatically correct and isn't really informing me as to what the question is. So I will not answer that.
You quoted numbers, right? Like, is that something from the, is it the MNIST data maybe, or?
So this is probably in the CFAR. Yes, okay. So this is, I was a bit confused with when it arranges it. Yeah, the numbers for each image are organized into a three-dimensional array called a feature map. And I was a bit confused as to what numbers means here in this context, because you've got 60,000 images in superclasses and classes within that. And then you've got the resolution, but then your 3 8-bit numbers per pixel representing RGB, which is fine. But then the numbers for each, so it means the RGB numbers for each image are organized into a three-dimensional array called a feature map. Okay, so that's what the numbers are. But then the first two axes are spatial, both 32-dimensional.
Yeah, that's like the size of your grid, like length and width. How many pixels are you gonna represent, like the featuring?
So would that just be constant at 32, 32, and then the RGB image in your?
Yeah, but I think in other, or like say earlier on, you'd have like 3x3 grids. You'd have like pretty small like grid sizes. And does it go through the convolution, calculate like what an actual convolution is?
I don't think it does do it, yeah. We'll come on to that, I guess. Okay,
Yeah, because I think it shows it for a smaller version though than the 32x32. But I'm pretty sure they're just, yeah, that's just your length and width. It's like how many pixels are is that feature or how big can that like feature be? Like how many different grid spaces?
Okay, because I guess there's no reason that needs to be constant within the data set.
Sorry, the input image might be I don't think it's necessarily the input image, right? Isn't it the features? Like okay, no, so each image has a resolution of 32 by 32 pixels. Yeah, okay. So yeah, I would assume in most neural networks, like through one way or another, you need to make sure that the inputs are always the same size,
Mhm.
even if they're not really. Um, but that will just be like the resolution that you're allowed to like represent the images in that you're putting in to classify.
Because I was trying to think of how this looks and whether it's just like a, like you say, it's got the spatial dimensions, and then you've got this. So it was like, obviously that. So if this was 3 by 3, but that's probably isn't going to like this in Markdown, and then you've got. Actually, that's not even true because that's each of these
Should,
would be a tuple, right? With the RGB values.
yeah, but shouldn't it just be one value for each of RGB? Or like, how does RGB actually get encoded? Isn't it just three values? And then sometimes you can have an alpha as well. But
Yeah. So what I'm thinking is that this is the image, and this is your first row in the image, and then there's 3 pixels in that first row. Yeah, etc., etc. But I don't know if that. Sorry, that should be 3.
oh, sorry, yeah. So if you've got 3 by 3, you should have 9 uh like sets of RGB values, you mean?
Yes. Yeah. So
Yeah.
that's how the image would be encoded. But then I sort of didn't get why you need these 2 channels at the start, I guess, is my question. Because that can be inferred immediately from.
Yeah, it's the size, the shape of the tensor. And
So you,
that, yeah, sorry, that would be fixed in answer to your question. You wouldn't be varying that by image in a data set. Like you would pre-process the data set into your dimensions. Like if it's the input image is 32 by 32, that every image will be like cut down into that resolution. Um, and sorry, the different thing is the features themselves. They get like grid representations, but they'll be smaller than the 32 by 32. They'll be like 3 by 3 grids, um, or like
so
maybe
that
slightly bigger.
so this is just a way of keeping track of the size of whatever comes next in this feature map.
Well, it's just the dimensions of the tensor.
Okay.
Like you need to encode width and height, and those would be the first 2 dimensions. And then for each pixel inside um, the 32 by 32, like each one of those pixels has its own RGB, like like the 3 or it's like when you're doing hex codes, you get like 2 values to represent red and 2 for green and 2 for blue. But each pixel, yeah, will have its own RGB value associated.
Yeah. So this is encoding as 3 8-bit numbers rather than a hex code, but so these should be
Yeah.
okay. Cool.
Okay. Yeah.
More of a just preparation thing than it is anything to do with the CNN specifically. Okay. Anyway, we've got this CFAR 100 dataset database, and CNNs have spectacular success. And the way that I do that is by splitting your hidden layers into convolution and pooling. So convolution layers search for instances of small patterns in the image, whereas pooling downsample these in some way to select what's most important in that area. And then, as is always the case in machine learning, you just do that over and over again, and for some reason it works really well. So the convolution layers, this section goes through like an example calculation to show you how it works, but I think it's quite useful to look at this in one dimension first and what a convolution is, and then it makes more sense in the image case, in your 2D case. So convolution, if you've got two functions, it's like passing them through each other and looking at what comes out. So this is the schematic here where you've got f star g, so f convolved with g, or the convolution of f and g, and you basically push them through each other and then see what the average is between them. I'm going to say average, I'm not sure it is strictly an average. And so I think having this idea of pushing one thing across the other and seeing what the total is quite a useful view of it when it comes to doing this in 2D. You're basically doing the same where you've got your filter and you're just running that across the image. And then you get out the convolution of the image in your filter. Whereas I think when it just says when you convolve this, I don't think this is clear that that's what that's doing. Well, I think this representation is just taken from the Wikipedia for this, and you get this. I think this moves quite quick, but you can see the same sort of thing where it goes through and just sums it all up, sums up the. You times the filter by the value in the pixel, and then sum up the value, and that gives you the individual value in your output of your convolution.
Yeah, that's quite a nice image. Well, like quite nice to have it moving.
Which I think makes it a bit easier to see than the 3x3, or the example they give there, 4x4 with a 2x2 filter.
Yeah, as in that's like, but it's basically like, you know what it's trying to represent is like, say you got that little convolution filter, and if you're just like grabbing it and just like stamping it, and then position for position, it's like alpha goes with A, like beta goes with B and stuff. Like that's what that's representing, right, in the convolved image. And you're just like stamping that filter on the places it can go. So that in the first one, because it's like 2x2, you do it over the first 2x2 like sub matrix or whatever of the original image, and then you move it one to the right and bang, stamp again, and then like you can't go any further, so you got to come down to the next one. It's like stamp.
Yeah,
stamp.
That's a good point you've made there. In this, they like had the array, so they put it on every element and like have these extra elements around the edge, which obviously in the book they don't do. They just say it can't go there. I think it does mention it in the book about like zero padding.
Yeah, you do padding. Yeah, because you don't want to not be able to use the information from like this. Yeah.
Yeah, which is why this convolved image gets smaller and the one in the GIF doesn't. Is because they've got that padding around the edge. Yeah, so convolutions are not unique to machine learning or image processing. They're used massively in a lot of signal processing and like signal analysis. And lots of mathematics basically comes down to convolutions in analysis. So yeah, a very powerful little tool that turns out to be really powerful here as well, basically. They do give this nice example of example filters that basically pick out things that are more vertical and more horizontal by using a filter that looks vertical and a filter that looks horizontal. And I think that starts to show how the network might learn features or what's important is because it does select that information from the image in some sense. Yeah, and so you do your convolution layer and then you move on to a pooling layer, which is how you're trying to move from your larger image into a smaller one and condense that information down. And you do a similar thing where you look across a subarray and you pick the biggest value. So that's max pooling. So in this submatrix 1, 2, 3, 0, the biggest value is 3. And so that takes the top left. In the top right, the biggest value is 5, etc., etc. And so it's a way of condensing that larger image down into a smaller amount of information. In terms of architecture, like I said earlier, as usual in machine learning, we just start to strap more of these layers together and convolve and pool, convolve and pool. So you can see here the convolution is keeping the same size, so they are doing some sort of padding, and then pooling is reducing it down, convolving is keeping it the same size, pooling it down, until eventually you end up with something very small, and then flatten it into your classification.
Does it say explicit? Sorry, I scanned most of this part of the book, like basically a couple of weeks ago. But does it say in the book explicitly, like the first layers, you see these like big convolution layers, and you kind of got like more, like you got like more small matrices. But earlier in the convolution layers, you get like the global features. So you almost would be like looking at like, is this like a cat or is this a basketball? Maybe in the first sort of layer, like picking out features that would help you determine that kind of stuff. And then as you go through the layers, you'd be like, okay, I've established this is like probably a feline now. Now I'm going to look at like the eyebrows to determine whether it's like a lion or a house cat or like a tiger or whatever.
I don't know if it did say it like that. I guess you're saying you go for the largest amount of information first, and then you refine down from there. So you try and make the most obvious choice at the first step, I guess. Rule things out.
Yeah, and your filters get more specific, like the more you go, because they are like they take as input, the previous outputs of the filters and the pooling layers.
Yeah, I don't think. Yeah,
I guess it kind of says like each subsequent convolve layer is similar to the first. It takes as input the three-dimensional feature map from the previous layer, and then it like does more and applies the next convolution. So maybe it doesn't say it as many terms. I just perhaps know that from like previous stuff, but that's kind of what it's doing. It's building up this like hierarchical, or like almost like reverse hierarchical thing where you get the top, like most general, and then throughout the layers you pick up on increasingly specific things. And that's kind of why it's so powerful for images.
I guess it's the same as like a random forest, right? Where you pick the biggest split to start with. And then
Yeah, similar principle. Yeah, what gives me the most information?
If
yeah, and I'll yeah.
Yeah. And then is each one of these blocks, if you like, is that a different filter applied to one of these RGBs? Because when it says you increase the number of filters, so is that the same as having more units in your hidden layer? Because each one of them is a convolution with a different filter.
More units in your hidden layer. So what's the question? I think I just didn't understand.
So you get more layers here. Sorry, not more layers, more matrices, whatever you want to call them. Each one of these is a unit, or it's the output of a unit in your hidden layer.
That's like a convolutional layer. So you do the convolve operation with like the input image, and then you get this like output, and then you pool it, and then you pass to the next convolutional layer. And that convolutional layer is, in this case, is like it has more filters, more small filters. It looks, in my mind, it kind of does look quite, if this is what you mean, like it's kind of, it's almost kind of different to this. It's like you put the input in, you get a small number of like, in this case, it would be like you put the input in, you get a small number of hidden layers, and then you get like a larger number of hidden layers in the next bit. And then again, you get like a larger in the next bit, and then you'd go to your output, but it's like you get your input, small number of convolute, like into the convolutional layer, you get a small number of filters in the direct, and then when you go to the next convolutional layer, you get a higher number of filters, and each of those like is more, it's focusing on a smaller part of the image than the initial jump into the like the first convolutional layer would be.
Okay, I think what I've realized is what is circles here is the squares in the one below. And so exactly what you're saying there, you do your convolution, but you do it with many different units here, many different filters, which gives you a bigger stack. Then you pull it down to fewer, and then you convolve it with loads more filters. Because the filters are taking place of the functions, where here we had our P, which was the number of units. No, sorry, not P. This 1 to 5, how many units you have in your hidden layers is the number of functions. Here we're talking about filters rather than units.
Yeah, because units I can find units kind of somewhat confusing, because a unit could mean like a hidden layer plus like a normalization or something. That could be like a unit.
Okay.
And like in this case, like a unit could be, in my mind, a unit could be a convolution and a pooling layer together. That could be like one unit.
See,
I don't know if that makes sense.
Probably a simpler. In this simple example, the units are just, I thought that scaled where the unit is just the function, but the unit is more things than that. I think you see that later on when it mentions LSTM, and if you look at them as units, there's actually a lot going on within that one block.
Oh yeah, yeah. Yeah, I won't say anything now. I'll wait till then.
Wait, so sorry, so I'm just gonna like ask a question here. But overall, it is more layers. You're like getting more convolution overall, as like in layman term. It is getting more layer, but then you're just highlighting like more features as you zone in more and more as the process goes along.
Yeah, each layer that you add, if we're saying convolutional layers, right? Each layer that you add will introduce like more filters than usually like the previous. So it doesn't have to. You could have it go a different way, but generally it would introduce more. And at each layer, as you go forward, you'll be like focusing on something more specific in the image.
Okay, cool. Charles?
Okay, I'll crack on, so otherwise we'll run out of time again. A big part that it mentions here is data augmentation. So when you've got images, you can mess around with your data basically and have similar looking things that you can use to train your network to be more robust. So you can do this by like warping or distorting images, zooming, shearing, rotations, or flipping, which gives you things that will have the same label but look slightly different, which are obviously the same to the human eye, but then help the machine learn that have difference at the same time, rather than focusing in on the eyebrows are always here for a tiger. It's trying to learn other features of the tiger that define it as tigery.
Yeah, it's like a tiger upside down. It's still a tiger. So like you do want to like learn that, yeah.
I wonder, there must be cases in which that's a terrible thing to do.
Oh yeah, in like if you're not doing images, like if you're doing words and documents, like if you've built a model that can understand like the order or where the sequence is important, and then you just go, you know what, I'm just gonna like switch around all this order, but I'm gonna keep the same label, is actually you just like destroyed any real chance you've got of learning.
Or if you were trying to train a classifier to say, is most of the action happening on the left or the right of this image? Which sounds like quite a trivial example, but I guess
you could literally just ruin the whole thing by rotating. Yeah,
probably good to be aware of just in case. And it also says this kind of fattening of the data is similar in spirit to ridge regularization, which I thought was quite a statement to throw out there. It doesn't really justify that. I think it's because you have do I think do I have an opinion on why that is?
Similar in spirit. Yeah, that's interesting.
Because my understanding is adding ridge regularization is trying to minimize the 2 norm of.
I can't remember if it's L1 or L2, to be honest, but
I think
I'm sure you're right.
last is L1. I may be wrong.
No,
I think I'm wrong.
Is it? I think in the sense of what you just said, I can see how it's similar. Of when you said like you need to figure out that it doesn't matter that the thing is like precisely here. Like you need to figure out that that thing can be in different places. Like you don't want to overfit kind of the idea that the eyebrow has to be in the 32nd pixel or whatever. Like in that sense, I can see how rotating and switching stuff is like in spirit similar. It's not mathematically similar, but it's trying to do the same thing. So it's trying to stop you overfitting the exact quirk of the input data as you see it right there. Like, I suppose that's what they mean.
Okay, I'll take that. The good news here is that you don't often have to train your own classifier from scratch. What you can do is take a pre-trained classifier, freeze the weights of the first number of layers, and then just update based on the last couple, which works really well when you don't have access to massive compute like the people who train these models do. Yeah, so you only train the last few layers yourself, basically. And they give an example of doing that using ResNet on their photographs.
Yeah, so this idea as well, like this is like the transfer learning idea pretty much. And this is why like just anyone or as any of us can sort of like do these tasks now, or like using LLMs for stuff. Like it's because we don't need to train all the layers. And in some cases, you don't even train any layers. You just add like a classification head and learn weights for that, which is even easier.
I don't think it uses the phrase transfer learning in this, but yeah, that's a.
Yeah, I think so. It's a pre-trained classifier. I suppose maybe transfer learning became, or at least I started seeing it as a term about 3 years ago, maybe 4 years ago. But I don't know if it was also a term before that they just don't use.
Yeah, I guess I don't want to introduce too much jargon. Anyway, moving on from CNNs, we get on to document classification, which is looking at text data. And so throughout this, they use the example of IMDb reviews, and you're trying to classify the sentiment of the review, whether it's positive or negative. I think this section in general is one of the sections that has probably been very massively impacted by recent developments, such as transformers and LLMs, because I think it's probably changed a lot how this would be done in practice these days, which
I never realized that, sorry, J.J. Allaire co-wrote the deep learning books with Francois Chollet. J.J. Allaire is the guy who like built the RStudio IDE, like owns Posit, the company.
Oh, really?
Yeah, I mean, he is an absolute monster. Like, if you ever hear his talks, like he's super smart. But I never actually realized he did that. Interesting.
Yeah, I've never heard the name before. It was some deep knowledge. And so the most common way, at least historically, was this bag of words model, which you have you get a dictionary of words, which can be very big. So yeah, in this case, an English dictionary, and you basically filter the text you've got for words that appear in that dictionary. I think what was probably the biggest thing to me here is this is when it starts to become. This is the first time it's been obvious the size of the vectors that you actually play with when you're doing this. I think often in textbooks it gives you examples of quite short vectors, but now it's like, oh yeah, this this is actually going to be 10,000 long, for example, 1,000 most frequently occurring words in 25,000 reviews, and you're sort of like, yeah, computers are cool, man. Even with images, when that's obviously quite big data, if you actually looked at the length of that matrix, it's just cool how much you can just sledgehammer and just use everything. I guess they have the size of this.
Yeah, in this case, it's like the vector as well is like a one hot, right, for bag of words, as in like
it would be m hot.
Oh, yeah, sorry, as in every single word in the document has a one in the place in the vector where it's like that word. And each word is represented by a one hot vector. Like that's just the way like a bag of words represents things. I suppose. Can you also have numbers like sometimes with like 5? Like if you have the word 5 times in the
So in this case, it's
document.
just absence. I think you definitely could use frequency use as well.
Mm.
That would be, I guess you might find if a review is a bit more on the fence and they're using good words and bad words, or things that you've learned as good or bad, so then you might want to see how many times you're using each one to try and give you an output.
Oh, sorry, it does actually say that in the book that one could instead record the relative frequency of words. It says only score a word is in or out of the document. But for example, one could instead record the relative frequency of words. So you could have the actual value, or you could have like a proportion of the, yeah.
And the key here is that most reviews will not contain anywhere near every word in the dictionary. And so you'll have a very sparse feature matrix, which means that you can store this much more efficiently because you don't need to store the whole matrix. You just need to store the locations of the non-zero entries.
And also when you compute, right? Like you don't need to calculate a value for every single one because the zero is just nothing.
That's probably an argument against, well, not against, but for why you might not want to store frequencies, because then you would also, you'd have to store the locations of the non-zeros and what non-zero value they are, rather than just the locations because you only there once if it was presence absence. And then it goes on to fit lasso logistic regression and a 2 hidden layer neural network with 16 ReLU units. I don't remember it defining ReLU, but maybe it was earlier on in the activation function section. I thought it only
We spoke
max.
about ReLU last week, right? It's 0 or 1. So if it's below 0, then it just everything's zeroed. And if it's above 0, then it's just the value.
Yeah, maybe I just didn't put it in the notes. Yeah, and you see that we get pretty good accuracy. I'd say similar accuracy actually between lasso and logistic regression and your neural network here. The comment is that both methods overfit the training data, but then achieve similar accuracy on the test set. Which again is quite cool to see that logistic regression was so good. I guess I said this last week. I was surprised at performance. Last week the difference was slightly larger, but here's like
I think in the history of deep learning and things, it took a long time and a lot of compute and whatnot, and a lot of researchers to just do better than these like bag of n-grams models. That was like decades worth of progress just to be like comparable to like a small bag of n-grams model, which is funny.
The reason that they're similar here is because a 2-class neural network is equivalent to a nonlinear logistic regression model. So I guess you'd expect similar performance. Yeah. A key point here is the bag of words treats words as individuals without context. As you just mentioned there, Jack, the bag of n-grams, where you're looking at pairs or ends of words. because some words that are negative on their own might become positive when used in combination or when you've got a bigger context. So the idea is that taking more context in, you get better output out. Yeah,
there's oh sorry, Carl. You know, you put like in the bit like there are at least two other ways to say maybe more now with transformers. Is it clear when you're reading the book, and this is just something I've picked up over time, it's like unless you do n-grams, so it's like if n-gram is 2, you've got 2 words in order. If n-gram is 3, you've got 3 words in order. And then you've got some sense of the order of the words. Whereas is it clear when you're reading the book that the bag of words models, like they have no ability to understand what the order those words happened in the sentence or in the document that you're trying to classify? Like it's treating it basically as a set. It's saying that in the document there's like these words somewhere, don't know where, like don't even care where they are. And if you think about that, like that means in language there are going to be times where you can't possibly get the answer right every time. Like the same exact words in a sentence rearranged can be completely different, say in like document classification.
Right. Yeah. I don't think it makes that explicit, but I think this is sort of getting towards it, where you're saying you're treating words as individuals, and I don't think I thought it did matter, and I don't know if that's from the book or just from feeling, if that makes sense, that would be the case. Like I had no reason to assume that it would take context into account in terms of position in the document as well as the word itself. I guess you could smash that into your feature matrix. Where does the word appear? If you
that is sort of what happens a little bit in later models, like transformers, you like positional encodings. It's a bit jumping the gun, but if you think about like why it matters, is like this. If you had the sense like this movie isn't terrible, it's very good, and you had like this movie, it's terrible, or like it's not terrible. Sorry, it's not very good. It's terrible. You know, like just the position of the not would completely shift the meaning of the document. Yeah. So if your n-gram model can't represent where that not is in relation to other things, then in principle it can't get it right every time.
Yeah. Or like if you had the cat sat on the mat, you just looked at the words, you wouldn't know if the cat was on the mat or the mat was on the cat.
Yeah. Yeah, exactly. You don't, and if that's important for the task, your bag of words model, though it might be simple, it's like, to go back to bias variance trade-off, like it's got high bias for that task. It can't, in principle, do it well, like consistently.
Yeah. That's super interesting to think of. Like the obvious cases that you've given there is like negations. And like, well, 2 grams would fix that, because then you would understand that it had been fixed as soon as you've got that extra word. But then,
not always though, because it was like if you had, depending on where the not is, the not might be, so you've got n-gram of 2, the not might be 3 words before where like it's quantifying over and stuff. So yeah, adding n, like increasing n, making it higher, gives you more structure, but also means your tokens are like really different. And like, yeah, you obviously don't want to get to the point where you're like n-gram model is like a full sentence, you know, like feeding in sentences as features. So it would be quite tricky to know. Oh, sorry.
In the n-grams, once you've chosen like your pairs of words, would it retain the order of the pair, or is it just saying that?
Yeah, that's why it has some. You get some information about the position of things when you use an n-gram model, because it is in order, like this, then that.
Okay, so it'd be like good not and not good at different positions in your feature matrix. Not that that's a good example, because one of them doesn't make sense.
Yeah, let's say if you had Moody is, that would be one engram. And then you'd have another engrams is terrible. So you would get from, because you've added that little bit of information, you would get like the not is in that sentence I gave, like the not is not with terrible. Because you've got is terrible as an engram. So then you could actually get that like small sentence right with engrams. Obviously, in real cases, it gets. I mean, there's just so many different ways that things can be said, or like sarcastically or whatever, and it's kind of hopeless to capture all of the ways that things can be said if you've got something like this engram model. Another one though would be if you were like predicting something like, I don't know, final stock price. Like, it's much better for you to know that what happens recently rather than know that at some point it dips 10% and at some point it dips like 5% and at some point it rises 20%. Like if you were just representing, say, like that information as a set, you would just have the number of rises up and down or whatever. But it'd be much better for you if you could take into account when they happened, because like dropping 10% from a higher number represents a bigger absolute drop than from like a lower number. And like all of these things pieced together would mean that if you can't encode the order of things happened, it's like you're not going to do as well as if you can encode the order.
Yeah, taking into account history, isn't it? And in any, whether that's the history of the text up to this point or the history of the process up to this point. Yeah.
And I mentioned that stuff because that's like the big motivation for like recurrent neural networks. It's like that's why people start building them or like making them or thinking up the architecture.
I see. Yeah, so this was sort of a general point in this section is we've talked about basically language models, but how much has it been changed by transformer architecture? And we sort of touched on this last week, that the book was from July 23, this Python version, but obviously the original book was earlier than that, so they don't cover that. And so we discussed covering something like transformers and attention next week, but we'll see. And so I thought this section was interesting where it starts on as if sequential data is something new, when it's just mentioned that text is sequential data or can be treated as sequential data.
Yeah, I suppose what it's going to try to get at is that like sequential data isn't necessarily new, but the techniques we've had so far, they couldn't use any of the sequential information.
Yeah,
or more or less.
Yeah, or we're treating it as if it wasn't sequential, when in fact you'd get a lot more from it if you did. And so some examples of sequential data, like we just said, text documents, any time series data, like weather, financial time series, speech, and handwriting. So what you've just written will affect what you're about to write, or the next character that you're writing. And so in recurrent neural networks, the input is a sequence, and the architecture aims to exploit the sequential nature of the data, similar to how convolutions exploit spatial structure in images. And I think that's a really interesting point, which seems kind of obvious, but you design the model to exploit structure in the data, which seems really key for any modeling you're doing. Or look at the data you've got and how can you make the most of any existing structure in that. And so you've got this compressed form of the RNN here, which I think is quite confusing, and it's much easier to think of it like this, where you've got your sequence input at each point, and then that gets fed back in or fed into the next layer for the next bit in the sequence. And you get an output at every layer, but you don't see them, you only see the final output, this OL. And this was an observation that neural networks look like linear models in a sense. And I was wondering if there's a similar representation of an RNN in terms of a time series model. So time series modeling, obviously a huge field of interest, given that it's, well, financial time series, weather, etc. There's a lot you can do without deep learning. and it does actually mention this later on, but it feels similar to what you call autoregressive models, where so in like an AR1 model, you look at the previous one thing that happened, and that informs what's going to happen next. And this is like an ARL model where you look at the L previous steps to inform the output of the last one, which I think it says explicitly later on. So each of your inputs is a vector. So it could be a one-hot encoding of a word based on your dictionary, and your weight is shared between the nodes. You only have one set of weights, and your loss function is just the difference of this output here. So you don't look at the intermediate outputs. And again, you learn by minimizing sum of squares. And a question here was, somewhere in here, it says that the X is a vector sequence. Is it here or is it further on? So, okay, here. So we use the lowercase letters, the observe yi, and the vector sequence is xi. It wasn't immediately obvious to me why this was a vector sequence. Because it kind of looks like it shouldn't be, being a lowercase and having two indices. But this xi, yi is an input sequence response pair. So xi is the matrix of inputs at each node of all of your inputs. And each one of these is a one-hot vector. So each one is a vector. And this is a visual representation of a one-hot vector, where most of these are 0, and you've got a 1. That is the value. I don't think you've got any repeat words. Oh, do you have 2 of those? Yeah, you've got a couple of those, and you can see they have the 1 in the same position. This is obviously a very small dictionary compared to your 10,000 long dictionary in the earlier example. I won't mention embeddings here because I think it comes up shortly. So again, we talked about document classification, and we've seen the bag of words. And so it's now trying to use the sequence of words or a sequential model. And as you probably expect, the dimension blows up very quickly when you start to include previous information. And so if your document's one-hot encoded to length 10,000, if you had 10,000 words in your dictionary, then there's 1,000 words in your document, then the dimension of each input would be 1,000 times 10,000, which is very big, and also would be mainly zeros. So to get around this, you can embed the word in a lower dimensional space, and hopefully as a dense vector in RM, so real numbers, rather than a one-hot vector. M can still be pretty large, so it says here in the low hundreds, which to me is large, but probably in computer science terms isn't very large. And that's what this visualization is showing at the bottom. So you go from a one-hot long vector to a dense, much shorter vector, and where the color is your real value between whatever real value that is. To create this embedding, you can learn it as the first step of your neural network, in which case it's an embedding layer, or you can use a pre-computed embedding, which is known as weight freezing. And there's examples there for words specifically as word to vec and glove or glove.
Does it help people? I don't know, do people think about like, but to think of that, the one hot vector, that is basically just like a lookup. Like you've got a different, say you got your embedding weights matrix or whatever, and you say you're getting them from glove or whatever they are, word to vec. Each word that has, like, say the first word is this, that is in like position 3 in the one hot vector. So in here. So then in your matrix of embeddings, you would have a different like, or like the tensor embeddings, you'd have a different matrix for every single word. So, or like a different vector representation for every single word. So you go into the third place and pick out where that is in your glove, and then you go like, okay, now give me the embedding for this. And it's like a lookup table. It's saying like, go in, find me that, bring it back. And then you like bring out this representation, this embedding.
That makes sense. It's a map from the one hot to your. It's a map from words to a dense representation of it.
Yeah.
Yeah. So then you do this and you get a sequence of vectors of length m, which will be much shorter than your full dictionary. It then says we limit the document to the last L words, and it wasn't clear to me immediately why that was, because then documents are shorter than L get padded with zeros up front. I don't know if that's just so we have a fixed length, I guess, and you could either take the first L words, randomly sample L word. Randomly sampling would be a terrible idea if you're doing a sequential. Yeah. But you've got to take the first or the last, and I guess they've chosen to take the last L words, and yeah, zero pad things that are shorter than L.
Yeah, that is something that is a choice they've made. That's not how like all RNNs would work or anything like that. It's not like a necessary truth, but it's something they've done.
Cool. And yeah, the key bit in this section is that the embedding layer is by far the biggest cost, learning that representation. So if you can get around doing that by using somebody else's, I think the recommendation here is to do that. And yeah, so this is only given you as like a simple RNN. There's obviously, like everything, much more elaborate methods, and the example it gives here is LSTM, which is long-term and short-term memory. So here in the RNN, you're only affected by the previous one. I think the idea of LSTM is to start to use information from earlier in this chain, rather than just indirectly as it gets passed through, to directly use that later on. I did look up a diagram of LSTM and thought it would be too confusing to get into and understand, so I'll just leave it at that.
One thing maybe to add is like for a standard RNN, you have that layer above, which is like the hidden state or hidden layer. That should be keeping information from all of the previous tokens.
Mm-hmm.
So you're like building up this representation of the entire sequence, rather than say just like the previous word.
Mm.
So you store it up in that hidden layer, but they might be talking about it here. But as the sequence gets longer, like that information gets increasingly diluted. So the first token, like when it's just the first token in the hidden state, is basically like all the information is from the first token. In the second step, like x sub 2, x sub I of 2 or whatever it was, like now you're diluting the information from both the words, and then the third one even more so. But you do keep this representation of the sequence with you in an RNN.
And I guess that's what it's calling short-term memory, is you only you have a longer term memory, but only through accumulated short-term memories.
Yeah. It's like, what is kind of funny because it's almost not also like short-term memory as well. Well, I suppose it is, because the most recent token like is multiplied, say, with like a dot product with the hidden layer. Mm-hmm. So it's like embedding is multiplied with the hidden layer. So it's like an average of those two. And that token is like there's more information from that token present in the output than there is from the previous tokens. But it does mention, right, like with the long sequences, that the early tokens essentially get completely diluted, such that if the really important word in the sentence is right at the beginning, it can be the case that no signal gets through, and you end up outputting the wrong prediction. And that's, like you said, that's all you're looking at. It's what does it output at the end? That's what you're going to like test as the quality of the prediction.
And I guess there's the scenarios where that's what you want. I'm trying to think of a process like a time series where what's most important is yesterday.
Yeah, where you want exponential decay. You want old signals to fade. Yeah.
If you're doing like weather forecasting, I want to know what the weather was 12 months ago, because I know that there's a cyclical nature to it, and I'm not going to capture that information if I only have, although maybe, yeah, probably not, but there's going to be bigger structures there that aren't captured from the previous.
Yeah, well, it's like it's with weather, maybe that's tough, but like say a similar thing about time is like if you were forecasting demand, it's really useful to know like what's the recent demand been normally, like what's it been the last day, what's the last week, not was it like 10 years ago. But if you don't know that like tomorrow is Easter, you know, and like you would have known to last if you know the patterns of the years, like when Easter falls, and you actually want to look back at what happened last Easter, because that's going to tell you how much chocolate you're going to sell in your shop. Like if you were just leaving that information out and you're just looking at the most recent information, you would completely like miss forecast the demand. So that's when it would be helpful for you to not have this property of like decaying of the signal throughout the steps, or just taking account of the recent stuff.
Easter must be a difficult one in time series data, because you just look at the date and you don't know that it's Easter. You'd have to work, when Easter was in that year.
Yeah, I should have used Christmas as an example, because you need a dummy variable for Easter with Easter.
Yeah, we're running out of time, but I've written very little about time series forecasting. And I think it's just using an example of, it says predicting the stock price is hard. If it wasn't hard, everyone would be rich or everyone would be poor. I don't know which way around that. But trading volume isn't so hard, and so they try and fit a model to volume. And they show, this autocorrelation is what we're talking about there. If you only cared about the previous day, you'd only have a spike at the first one, and then it would drop off immediately. But here you're seeing that there is this decay in how relevant previous information is. And I think this is where it talks about AR models somewhere.
It's just a bit further down, I think. Maybe a slide or two.
Okay.
It does show it on the next one there. Yeah, there you go, auto regression.
Oh,
I would say it's maybe not even worth us, like, say if we're going to continue next week with deep learning, even focusing on like RNNs for prediction. I would say generally like people, they're not like competitive. Like you should use like an ARIMA or a seasonal ARIMA or something. Like it's kind of mostly what people are still using.
Domain specific model rather than
and just one that's it's built specifically for time series. And maybe you want to add features and stuff yourself, and maybe some of the features could be given by like the output of a neural network, but for the actual like time series forecasting, don't quote me on this, but I feel like there's nothing where it's best to use an RNN, but that could be wrong.
I wouldn't be surprised at all. Okay, from here, again, conscious of time, it's kind of interesting when to use deep learning. Just use them. I think they're quite conservative on them. And they say, it's been impressive, but they're only good for this set of problems. So image classification and things. I think if you believe the hype at the moment, it feels like they're good for everything. But like you've given a really good example there, Jack, of a time when you might not want to use deep learning and actually use a more traditional model. But it does say if you've got a lot of data, then deep learning is probably a good thing. But it does give an example where linear regression outperforms a neural network despite having 2 orders of magnitude fewer parameters. And I will stop there before we start diving into how you actually fit because that will get spicy.